Hello, I'm Rod Elmore, and today we're going to talk about counting. You might not think you have to count, but I've got 4 problems here, and these 4 problems we have to know how many outcomes there are in each case, because the next step after learning how to count is probability. And if we don't know how many outcomes there are, we can't figure out what the probability of that event happening is. So we've got 4 problems. And the first one, we're going to use a tree diagram. So the first method we're going to talk about is a tree diagram. Now don't dismiss this, because a tree diagram is a lot, people think it's silly, but let me tell you something about it. When I grade the test that you're going to take, half of you won't be able to do this on the test. That's what statistics tell me. And that's, of course, this class. So even though it looks really simple, kind of ridiculous, it's kind of a powerful tool because it does show us the actual sample space. So let's just try this first problem. So reading number 1, using a tree diagram, determine the number of outcomes for the following sequences of event. A couple has 3 children, and we're not going to allow any twins or triplets, and we're going to assume that there's a 50-50 chance of getting a boy or a girl. So how many ways can this happen? How many ways, outcomes can there be for this? Well, let's take a look and see. Now we're going to use a simple tree diagram. We're going to first say, well, we got a couple here. So we've got a boy and a girl. So in the first round, they could have a boy or a girl. Second round, they could have a boy or a girl. Down here, if they had a girl first, they could have a boy and a girl. Now, so they had one boy. If they had another boy, then there's still a 50-50 chance of a boy or a girl. 50-50 chance of a boy and a girl if they had a boy, girl, girl down here. Then we've got 50% chance here. Now, doesn't this look ridiculously simple? Why is it that so many of you are going to miss it? Because you're not going to practice. It looks too easy. So now we have a simple thing. How many outcomes were there? That's all we're after. How many outcomes were there? Well, let's see. There's 1, 2, 3, 4, 5, 6, 7, 8. So there's 8 outcomes in this particular problem. And if we actually looked at this, at any one of them, it would tell you. For example, right here, what would have been the situation? A girl, a boy, and a boy, right? So then we could ask ourselves, how many times of these 8 outcomes has 2 boys and a girl, for example? How many outcomes have 2 boys and a girl? Well, this one I marked has 2 boys and a girl. How many other ones have 2 boys and a girl? Well, girl, 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 that's not it. Girl, girl, boy. Girl, boy, girl, that's not it. Boy, girl, girl. Boy, girl, boy. That one has 2, doesn't it? So then we have boy, boy, girl. This one does. But this one's boy, boy, boy. So we're able to count, and there's 3 out of the 8 that are 2 boys and a girl. So we're able to count this. We're able to look at our sample space, see all of our outcomes. Now, if this was a lot more choices, you could never use a tree diagram. But don't forget how to use one. And in simple little problems, use it to answer your questions. And we'll see that in the next section. So that's using a tree diagram, a simple thing. What do a lot of people do? They just separate these out, some silly thing like this, and they don't connect them. They've got to be connected. So make sure you practice one of these. Okay, that's a tree diagram. Used it for counting. Number 2, the fundamental principle of counting. And we could use, let's see, for this one we can use, let's say we have a baseball team and we have 9 players. And we're going to do number 2. How many ways can a baseball manager arrange a batting order of 9 players? So if he has 9 players, how many ways can he arrange those 9 players in a batting order? Well, let's see. fundamental principle of counting says it's a product, and product means multiply, of individual choices. Product of individual choices. So let's see. The manager has to decide who's going to be first, right? So he's going to have to make how many decisions? 9 decisions. So how many choices does he have for this spot? 9. But if he's got a guy already picked to start, then he's got what? 8, 7, 6, 5, 4, 3, 2, 1. Because he has no choice on the last one. And the fundamental principle of counting says it's a product of individual choices. So then it's that many ways, and that turns out to be, he could have his order be 362,880. You can double check that on your calculator. But there's a lot of ways he could make that arrangement, couldn't he? So that's using the fundamental principle of counting. But when we look at this, there's another way we can display that. Right away you're thinking, man, we don't want to write this every time we see that type of thing. So there's another way to write this, and that's called 9 factorial. This symbol is factorial. It's an exclamation mark is all it is on your typewriter or your calculator, but it means factorial. And what does it mean? It means that if you start at 9, whatever this number is, you go 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. So if you had 4 factorial, it would be 4 times 3 times 2 times 1. So this is kind of an easy way to write this. And that this is 4 times 3 times 2 times 1. So then next, so we have this symbol we're going to use from now on, factorial. So number 3, we've got, let's see, we've got the tree diagram, fundamental principle of counting, and our symbols that we had, our factorial, we're going to be kind of using that here. It's this, and this is called a permutation. That should be an E, not a permutation. So we're going to use this symbol. Now, when we're going to use this symbol, it's going to have to deal with problems that where order matters. And I'm going to put the last one up too. And the fourth one is combination of n things are at a time. This is a combination. Combination. And this one, order does not matter. So those are our 4 techniques. So let's try, let's take for that baseball one, for example. Now there's a formula for this. The formula for permutation of n things are at a time. We'll put the formula out here. And that's would be n factorial over n minus r factorial. The formula for a combination is n factorial over n minus r factorial, r factorial. So this is a combination of n things r at a time, and this is a permutation of n things r at a time. So let's see, these are when order matters, this is when order not matters. Let's go back to our baseball one. Our baseball one said we're going to take n things. In that case, it was 9 things. And how many were we taking at a time? 9. So that would have been a permutation of 9 things, 9 at a time. Let's use that formula. So let's see, the n is 9, that goes on the top. The n is 9 here, and 9 there. And then 9 factorial, we know what that means. It's 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And then n minus n is 0 factorial. Now there's a problem. What does 0 factorial equal? Well, it seems like it should be 0, but no, there's one way not to take anything, so that's really going to be a 1. And so we end up with that same answer we had before. It was multiplying all of those out. So that worked. Now let's try some other problems where we get to pick and choose here. So on the video homework, if you take a look at that, the next problem is, how many ways can a committee of 3 people be selected from an organization with 15 members? So now we have a committee of 3, picked 15 of them. So how are we going to do that? Well, does order matter when you pick a committee? You got to think about that. Does order matter? When the baseball lineup, the order mattered. But in a committee, the order doesn't matter. So it's going to be a combination of 15 things, 3 at a time. So now let's just use our formula. Now we got to use our formula. We can't think about this one. If you decide you're going to use combinations, you're all done thinking. Permutations, we wouldn't need a formula. We don't need a formula for those. But combinations, as soon as you say order doesn't matter, you got to use a formula. So we're going to have 15 factorial divided by 15 minus 3, or 12 factorial, times 3 factorial. So we did it just like the formula says. Now let's see if there's an easy way to, you can do this all in your calculator, but I grew up doing these by hand, so I think they're not that bad. 15 times 14 times 13 times 12 factorial. Well, you already got a 12 factorial down here, and you can cancel those. And then what's 3 factorial? 3 times 2 times 1. Well, I can take the 3 and go in there 5 times, the 2 go in there 7 times. So then all I got to do is multiply those out, and I got 455 different ways of taking out of a club of 15 people, selecting a committee of 3. So this is a combination because order didn't matter. This is a permutation because order mattered. Now let's look at one more, and you decide which way it is. Now the way to do this is always go down from the top down. If you find a way that works, stop there. So let's try this last one. How many license plates can be made using 3 letters followed by 3 numbers? 3 letters, 3 numbers. How many license plates could be made there? 3 letters. Which way are you going to use? A tree diagram? Well, it doesn't seem like we're picking that way. A fundamental principle of counting? Maybe. It's a product of individual choices. If you had to make license plates, could you pick and make individual choices? I think you could. So let's try that way. So let's see, we got 3 letters followed by 3 numbers. So we're going to try that product of individual choices. How many choices do we have here? Well, there's 26 letters, so you use 26. It's a product times 26 times 26. Now we've got numbers. How many numbers are there? Well, there's 10, counting the 0. So we've got 10. So that multiplied out, which you can multiply out, will give you the number of license plates you can make. And you can see that with the license plate, they're adding more letters in, because if you put more letters in, it's a bigger multiple. So you can get more and more people. In the old days, it used to be 1 letter followed by 3 numbers. And so, but then couldn't have very many license plates. So they've increased the number of letters. So you got to try the video homework problems and the other homework problems. Think about these things. A lot of what you do in math is think about what your different methods are. As I call it, your toolbox. And if you know your toolbox, then you can use your brain to figure out how to do these problems. But these take practice. So try your video homework, and thank you.